Chapter 3, Exercise 17. Hints. Prove that this and that for all n equals 1, 2, 3, and so on. Prove that this. Solution. We note that xn greater than 0 for all n equals 1, 2, 3, and so on. Indeed, x1 greater than square root alpha greater than 0, and if xn greater than 0, then the following. Next, we obtain two useful relations. Relation 1 is this. As a consequence, if xn greater than square root alpha, then xn plus 1 less than square root alpha, and if xn less than square root alpha, then xn plus 1 greater than square root alpha. Relation 2 is the following. A and B. We prove by induction that this, for all n equals 1, 2, 3, and so on. Consider the base case n equals 1. By assumption, x1 greater than square root alpha, the relation 1 implies x2 less than square root alpha. The relation 2 implies this and that. Assume that the statement of induction holds for n. Since x2n less than square root alpha, the relation 1 implies this and that. By the relation 2, this and that, we have proved that this and that. C. The sequence x2n minus 1, n greater than or equal to 1, is monotone and bounded. By theorem 314, there exists a limit y equals limit n to infinity x2n minus 1. Note that y greater than or equal to square root alpha. Using the relation 2, we obtain the following. That is, y equals square root alpha. The sequence x2n, n greater than or equal to 1, is monotone and bounded. By theorem 314, there exists a limit z equals limit n to infinity x2n. Note that 0 less than x2 less than z less than or equal to square root alpha. Using relation 2, we obtain the following. That is, z equals square root alpha. Given epsilon greater than 0, there exists an integer n such that for all m greater than or equal to n, we have this and that. Let n be greater than 2 big N. If n is even, n equals 2m, and m greater than or equal to n, and this. If n is odd, n equals 2m minus 1, then m greater than n, and this. In any case, absolute value xn minus square root alpha less than epsilon when n greater than or equal to 2 big N. It follows that limit xn equals square root alpha. Both sequences, x2n and x2n minus 1, converge to square root alpha. D. Put epsilon n equals absolute value xn minus square root alpha. We estimate this, and we continue, where beta equals square root alpha minus 1 all over 1 plus x2. We prove that epsilon n less than or equal to beta to the power of n minus 1 epsilon 1 by induction on n. If n equals 1, the needed inequality holds with equality. If this, then that. So, epsilon n less than or equal to beta to the power of n minus 1 epsilon 1 for all n equals 1, 2, 3, and so on. Approximations for square root alpha from this exercise converge slower than approximations from exercise 16, since limit n to infinity n over 2 to the power n equals 0, theorem 320d. As an example, let alpha equals 3, x1 equals 2. Then x2 equals 5 over 3 and the following. Indeed, we have this and that. It follows that the following. Here we used the inequality 1 less than square root 3. In particular, epsilon 5 less than 1 over 3 to the power 4 equals 1 over 81, and epsilon 6 less than 1 over 3 to the power 5 equals 1 over 243. Obtained estimates are much greater than the ones from exercise 16. Let alpha equals 3, x1 equals 2. Blue points correspond to approximations from exercise 16. Red points correspond to approximations from exercise 17. The approach to approximate square root alpha given in this exercise is the method of finding a fixed point of a function here. Note that the only positive fixed point of f is square root alpha. See exercises 522, 524. Thanks for watching.